Well, okay, so I think we can start. Now, last time we started looking at the Landau levels. And essentially what we were doing was this. Our first treatment of an electron moving under the magnetic field was basically doing this semi-classical approach. So we have this. So we solved this equation, and from here we were able to explain the Haas 1-alpha effect. So the idea here was, as you apply magnetic field, the magnetic moment of a metal oscillates with the increasing magnetic field. And the idea is basically, under the influence of the strong external magnetic field, electrons take orbitals like this, and whenever the angular momentum, the magnetic field created with these orbitals, align with the magnetic field itself, you get an increase in the magnetic moment. Whenever you destroy this state in between, we show that these orbitals will be quantized. So when you cross beyond that quantization condition, then the magnetic moment of the material decreases. So this is one thing that we could understand doing this semi-classical approach. But we can do better than that, because we are equipped with the Schrödinger's equation, and I'm going to write time-independent Schrödinger's equation. Okay? And this guy, now you should get used to this, is our Hamiltonian operator. And we show that this guy is, it's basically sum of kinetic energy and potential energy is, I should get rid of this one, for a particle under the magnetic field. Oops, this should be A. Can be written like this. Okay, so the reason for this was electromagnetic field carries momentum. And we have shown that this is in fact the case. So if you have an electron under the influence of an external magnetic field, it will do a circular motion. And because of this motion, it has a charge. The field that rotates with this electron will carry a certain momentum, and we have to factor that momentum into our expression. Now, where we are headed with this is, once we solve this equation, we will see that because of the magnetic field, electrons will gain new energy levels. So if you take a metal, a piece of metal, what we had from our band model was something like this. So this is the energy. I don't have to draw K. So this is the edge of my Fermi level. And what I was dealing with was basically electrons right at the Fermi edge. So they were acting as if they are almost free electrons. But now, with the introduction of magnetic field, we will see that there will be new states appearing that we can control. So I'm going to get rid of this. And last time we started solving this equation. So what I would like to do is write this expression for a 2D slab. So I have a material in 2 dimensions, and it has 0 thickness in Z, simply because I'm not interested. I mean, we can give it a thickness, but I'm not interested in that direction. But also we have this uniform magnetic field along BZ. Then for this vector potential, which which was a quantity that we defined. So let me write it as a vector. It turns out that there are several ways to write this vector potential. One way was this. So I have, sorry, I should write it the other way around. So I have A, my vector. So let me get rid of this. So I'm going to have position in Y, and then this was pointing in x hat direction. Okay, so my A vector, this is one of my choices that I can make. The A vector is y, b, x hat. So what I'm going to do is I'm going to plug this in here. So y, b, x hat. And then write this in such a way that I can solve the Schrödinger's equation. So last time I think I have come to a point where I had an expression like this. So this was the things that I have done in the last minute. So I have the second time derivative of the wave function plus I have h bar squared kx squared divided by 2m. If you remember, the condition that I imposed was, okay, this is my total wave function. So since I leave electrons free in x direction, I can say electrons in x direction is going to be like a plane wave, okay? And then also I'm going to have, let me make it this way, a function in y. So it allowed me, when I plug this equation into one of the final forms, just a step before this one, I get this kx expression. Then I have h bar kx e y b divided by m. Then I have plus e squared b squared divided by 2m y squared. And then the energy expression is, I'm going to add EZ here since we have energies that are subtracted from there. Also, I have the wave function here as well. Now, it looks extremely complicated, but indeed it is not. So this part here is something that I can write like a simple harmonic oscillator potential. In the case of simple harmonic oscillator, we have such a potential, okay? X is any dimension. Then there is the angular frequency of the oscillation and mass of the pendulum, if you like. So I can write this expression in a similar fashion to that expression, and here's what I'll have. 1/2 m omega squared y squared minus, oops, sorry, no, not y squared, lb squared kx squared. And here my omega is EB over n, and this LB is square root of h bar over EB. Okay? So, I'm sorry. Not even x, y. Thanks. Okay, so now this is called cyclotron frequency, and this is the magnetic length. So if you really take the square of this guy and then put omega in the expression and LB in the expression, you'll see that we have the exact thing in this parentheses. So this one is slightly different than this, but what it is telling us is that this is a pendulum not located at the origin, so it's not oscillating with respect to x equals to 0, but it's oscillating with respect to some shifted point. So it's like if I take, so this is my pendulum, okay, so this is the origin. Let me say this is my y-axis, this is 0, then I wouldn't have this term. So what I do is I shift this pendulum to LB squared kx, and it oscillates with respect to this point. That's all. So I have this shift. Okay, so quantum harmonic oscillator is something that we can analytically solve. I mean, it's a textbook thing, but let me show you, first tell you that the magnetic length, so if you apply 1 Tesla to an electron, then LB is roughly 25 nanometers. So this should give you a rough idea about the scale of magnetic fields that we will be working with. So it's going to be on the order of a Tesla. And Tesla turns out to be, 1 Tesla is actually quite a strong magnetic field. So if you take the Earth's magnetic field, it's 1/10,000th of 1 Tesla. So it's a very large magnetic field indeed. Okay. Now let's continue solving for Landau levels. Now I have this simple harmonic oscillator, and let me, yes?
I don't get the idea how you would get a simple harmonic oscillator to this geometry.
Okay, so now it's not the geometry itself, it's the motion that electrons perform. Okay, so when you write this down, it turns out that the motion is very similar to simple harmonic oscillator. Motion of the electrons. Okay? So, I mean, it's much easier to show it from the equation. I'm not going to be able to really show you the motion of the electrons, but really they're doing this oscillatory motion.
Furthermore, we use this equation.
What's that?
Furthermore, we use this equation.
Well, so what I do here, so this one is this expression in the brackets. And if you like, I can show you that it's the case. But it's just a straightforward algebra. Just take square of this. Yeah, and so you will get 2y squared. And if you write this back in here, we will have e squared, b squared, m squared. So it covers this expression. Then we'll have 2m omega squared y minus m omega squared y lb squared kx, which covers this expression. And then square of this, lb to the 4th power, kx squared, mv squared, it will cover this one. Okay, so this really looks like a simple harmonic oscillator that's oscillating with respect to a shifted point. Okay. So, and these kx values, they're just the wave number in x direction. Now, let me write down the final expression. So plus 1/2 m omega squared y minus lv squared kx squared. I have phi here equals to E minus EZ phi. So there's one extra piece of information that I'm going to insert. Since I'm assuming, I mean, this is not too critical, but let's say this length is Lx and this length is Ly, then I can assert that the Kx is going to have quantization coming from the limitations of this two-dimensional plane. So I'm going to have another integer that will come into play, so it's just going to be first let me write this down. It's going to be what am I missing here? Just a second, I think I have a mistake in my notes. Check this from here. I think I have a typo. I don't want to write the wrong thing. Okay. So it's going to be j pi over Lx. So then this j dot is an integer. And for solutions of the harmonic oscillator, we already know the solution. I'll show you how to get this result in a moment. But for now, trust me that the energy values will have this form. So there will be 1/2 plus n, where n is again a whole number. Okay? So we'll have quantization of the energy values, just like in a potential particle in an infinite potential well. But this time, if you look at, if you think about the harmonic oscillator potential, it is something like this. It goes with x squared, okay? And the wave functions, if you consider the wave functions, will have tails that are extending slightly beyond the potential itself, okay? And again, you'll have higher order levels. So the energy of each level will follow this formula. So with that, we can also write down that this expression. So as you will see, LB squared, now Kx. Actually turns out that because of quantization in x direction, we have another index, J. So we'll have this general expression, J pi h bar divided by m omega L x. So if you like, the origin that this simple harmonic oscillator oscillates changes with the energy level of the quantization coming from the x direction. Is it clear? We have two quantization, one coming from the magnetic field itself, two coming from size confinement in x direction. Now, these energy levels are called the Landau levels. Okay? So they're discrete energy states that purely emerge because of the applied external magnetic field. And if we Now let me write this down. So for now, let's only stick to these En values. For E0, where n is equal to 0, the energy value is going to be h bar omega over 2. Or more explicitly, we can write it as h bar E B over 2 n. Okay? So it's a function of magnetic field. This is the electron's mass. If you like, it's the effective mass. It's not the free mass because we are dealing with a material. But the electron's charge and Planck's constant, they are constants. So the energy of each state depends on the magnetic field and type of the material you have. Then we'll have E1, which will be exactly separated by the first energy state by an h bar omega. So the value of this one is 3h bar over 2. And the separation between each energy level is the same. So this goes like that. So separation between each energy level is exactly h bar omega. Okay? Now, questions?
What do you mean by saying that the origin of the oscillation
Mm-hmm.
is also quantized and changes with the J number, which is coming from the
Mhm.
boundary of
Yeah. So basically, this is telling us that now the orbitals that these electrons take, if you like, depends on the k value along x direction. Okay? So it's difficult to visualize because we are tempted to think that this is really taking in real space, but this shift, we have to think it as collection of electrons having these circular orbits. So
Is it like this? I imagine that, I mean, in the y direction, there are a couple of circular electrons that are doing circular
Mhm.
motion, and these are discrete, at the discrete position.
exactly,
And their radius is also as well confined with discrete.
exactly,
H
yes.
bar omega.
Yes.
So can I think like this? I mean, in the physical world, is it what is happening?
I think this is accurate, but of course, yes, I think we can safely say that it's an accurate picture. But I'm not sure what really we can learn by just imagining that. The essence is that we create new energy states because now going back and forth between a real physical picture and its consequences might become very confusing. So the real result, end result, if you like, is that because of the magnetic field, we get another quantization, okay? And this quantization will be in parallel with the quantization coming from the size confinement, okay? So, and this size confinement, if you like, the length in the x direction determines the point where this oscillator oscillates about. That's all we should be saying about the Landau levels themselves. Okay, so we'll have slightly shifted positions for the oscillator. Okay. Any other questions? Now, let me see. Now, before proceeding with its deeper connections with with how we can study materials, there's one more thing that I have to introduce. Because as we are dealing with electrons under magnetic fields, it's something that we have to take into account. Or perhaps I should say, what I'm going to show is for most of the materials, it's not something that we should take into account because there are factors that that saves us from the trouble. So it's called the Zeeman effect. And if you like, I can add a spin in front to be more precise. Basically, Zeeman effect is when you put large enough or large magnetic fields on an atom, the energy levels split because of the spin of the atoms. Now, the reason is twofold. Electrons carry spin, and if we consider the z direction, there are two spin configurations that they can take, spin up and spin down. And you can imagine the spin as small magnetic moments. Okay, so they're like small magnets. When you put an external magnetic field, this will create a torque. I mean, of course, when they're aligned, it won't create, but there will be some spin precession. So the energy will be given by the magnetic moment times, of course, these are vector products, dotted with the magnetic field. So this is the potential energy of this configuration. Now, for spin up and spin down, it turns out that there will be a splitting in the energy values, because if you take the dot product, one will have a negative energy, the other one will have a positive energy. So the splitting will be twice the value of this guy. So what does that mean? If I write the Schrödinger equation, let's say even I have a free particle, then the expression is going to turn out to be the free particle part plus the potential energy because of this applied magnetic field that emerges from the spin. So I have to take this into account. And the end result, if you solve this thing, the energy splitting will be something like this. So this magnetic moment is, let me write down the splitting, will be a G factor. This is called the lambda G factor. Vaguely speaking, this denotes the difference between these two states, and for electrons and atoms, this is roughly equal to 2. Okay, so it's a factor that comes from the orientation of the spins. And then I have EH bar divided by 2m times b. So this mu, if you like, is basically minus EB times the spin of the particle. So if you plug in the expression for spin 1/2, then you have EB 1/2, then H bar comes from the energy value, and then we have B, and this lambda G factor is the factor that determines the energy difference between spin up and spin down configurations. And for, again, electrons and atoms, or free electrons, this is roughly equal to 2. There's some correction factors, but this is the energy splitting that you will get. So this means each of these energy values is going to have different energy levels depending on the spin orientation of my electron. If you consider this, now let's say I have a spin up electron in E0, then this electron is going to have, now let me write this correctly, because it's dangerous to work in the ground level. Let's say I have two electrons, okay, one spin up and one spin down. If this guy has the Landau level E1, then it is going to have this much more energy because of the spin splitting, E, G, E, H, or 2mB, compared to this one. So this is in E1. But if you look at this expression, let's say that G is 2, then this guy is H bar E B over 2m. Since this is 2, these two will cancel. I'll have H bar E B over m, which is exactly this. So indeed, a spin-up electron at E1 is going to have the energy of a spin-down electron at E2. This is a complication that should have been taken into account, but we haven't done this because in real materials, this is not true. Indeed, I can give you an example of common materials like that are used in such experiments. So, for instance, for gallium arsenide, Zeeman energy, so the splitting energy is 70 times smaller than the Landau levels, or if you like, cyclotron energy. So that H bar omega is 70 times more stronger than this splitting. And the reason is G factor varies due to the effects of band structure. So an electron inside a material has a so much modified G factor that this energy splitting becomes pretty much meaningless within a material. So this is something that you should keep in mind. It will pop up for when we study fractional quantum Hall effect, because the reason is when you have this G factor that is comparable, or this splitting comparable to the Landau levels, then we'll see this intercrossing of energy levels will result in very complicated paths within the material. So this is something that you should keep in mind. Okay? Now, let's look a little bit more about the Landau levels. So, you can write down that the wave function of an electron is localized around, so I'm talking about an electron at so any kxj value, so I'm going to add this j as well, or let me get rid of this 0 altogether, so yj, that's going to be minus k l b squared. Okay. Yes. Okay. So now what I would like to do is I would like to look at the, of course I have this J here as well. Now I would like to find the number of states per each Landau level. Okay, so if that's the case, then I can say for a particle that is confined within 0 to Ly, which is, I got rid of it, but the length in y. Okay, what I'm going to have is, so if I go to K space, I'm going to have something like minus Ly divided by Lb squared K 0. Okay, so let me redraw this thing. So this is my Lx, this is my Ly, this is y, this is x direction. Okay, so here I know that I have my kx to be 2 pi over Lx. Okay, and for Ly I have that quantization condition. So what I'd like to do is this. To be able to find the number of states, I need to multiply available states in x direction times available states in y direction. So this one is 2 pi over Lx. Obviously, I have kx. Then times, for this one, since my energy values in y are restricted by this lower bound, I take my integration from minus Ly over Lb. This is a slight approximation that I have to make, but it will turn out that it will yield an exact result since there are no states beneath that. So I'll just integrate all over these energy states. So what I'll end up with is something like this: Lx Ly divided by 2 pi Lb squared. And if you consider this is the real physical area of that whole surface. So I have an area A. Let me denote this area with an A. And then this Lb squared will give me Eb over 2 pi h bar. So this is the number of states that are available per each Landau level. And if you take a look at this, there is no quantization here. This is a continuous expression. I can continuously change with magnetic field B. My sample size area, or my sample area, is important. Then I have EH bar. But there's something interesting there, which we have seen before. Let me explain what that is. So, the title. So I can write that number of states as BA over, and this is exactly 2 pi h bar over E, or h over E if you like. And what was this? I mean, it's very, very obvious that I have magnetic field area Yes, quantum of magnetic flux. So, magnetic flux quantum. So the minimal package that you can have. So what is the message we got here? I have a sample's area, then I have a magnetic field, so there's a total flux coming through my sample, and the number of available states is basically an integer multiple of magnetic flux quantum. So each electron basically defines a magnetic flux quantum. The orbital that they take is an integer multiple of the magnetic flux quantum. Okay? And this is not surprising because we quantize the motion of the electrons, and we have seen this before in our semi-classical approach. The path that they take, the area that they enclose, only allows integer multiples of h over e. So it's quite expected that the number of available states is going to be integer multiple of the magnetic flux quantum. So with that, we sort of finalize how the Landau levels will look like under varying magnetic field. So I'm just going to copy the same graph here. This is the energy. Now I can write B here. Okay. Then so I have